A few weeks ago, I watched a woman walk into a high-end diamond exchange carrying a velvet box like it was a holy relic. She was there to liquidate an asset, her words, expecting the forever value the brochures always promised. 5 minutes later, she walked out looking like she'd seen a ghost. The offer she received wasn't even a fraction of the retail price. It was a rounding error. The appraiser didn't even bother with the romantic backstory. He just tapped a digital spectrometer and shrugged, "Carbon is carbon, ma'am. And right now, carbon is coming out of Henan by the ton." It's a brutal awakening for the luxury world, but the real story isn't in the jewelry store. It's in a dusty industrial corridor in China known as the Zhengzhou Zhuchang Shankui Triangle. For 60 years, this place didn't care about engagements or red carpets. They were obsessed with industrial grit, the kind of diamonds used to tip drill bits for oil rigs or solder reinforced concrete. But then the technology shifted. I recently saw footage from one of these Henan facilities. It's not the sterile, futuristic lab you'd expect. It's loud, heavy, and visceral. Rows of massive, six-sided hydraulic monsters called cubic presses, grown under thousands of tons of pressure. An operator in a simple work uniform pulls out a rough crystal that looks like a piece of glass, but it's actually a structural masterpiece grown in a 14-sided habit that mimics the Earth's mantle more closely than any natural stone ever could. What's truly unsettling for the old guard is the logic behind it. In Henan, they aren't crafting gems, they are outputting a commodity. They've cracked the code on HPHT, high pressure, high temperature, achieving D and E color grades that make Western lab-grown methods look inefficient and structurally inferior. It's a total collapse of information asymmetry. When a handheld tester can tell the truth for $50, the scarcity narrative doesn't just bend, it breaks. We are witnessing the moment diamonds stopped being a symbol of eternal love and started being the foundational material for the next generation of high-power electronics. This isn't a story about cheap rings, it's about how a legacy of industrial grit built a global monopoly on the most hardest material in the universe.
That is a really powerful way to open things up. It just perfectly frames the entire conversation we're about to have.
It felt powerful watching it happen.
Yeah.
And honestly, that image of her face, it just stuck with me. But as I started digging into all this, I realized she's almost a footnote.
She's collateral damage in a much, much bigger industrial shift. The story isn't about her ring, it's about the factory that made her ring obsolete.
Exactly. This isn't really about jewelry, is it? We think diamonds, we think romance, luxury, but that's not the real story here.
No.
Yeah.
If you stop at the jewelry counter, you've missed the entire point. The jewelry market is, just the visible tip of this massive iceberg. An iceberg that goes down 60 years.
60 years.
Yeah, 60 years of industrial policy, of state-backed research, of applied physics, and it's all centered on one specific place.
The Zhengzhou Zhuchang Shankui Triangle in Henan province. A place I'll admit I couldn't have pointed to on a map before we started this deep dive.
And most people can't. There's no reason they would. But that triangle, that dusty industrial corridor, it now controls the global supply of the hardest material known to humanity.
That's a staggering thought.
And today, what we're really going to look at is how that happened. We're talking about a 60-year industrial evolution that turned what they called a small county into the global diamond capital.
And we're going to get into the physics of it all. How a factory can actually mimic the Earth's mantle.
We have to. The technology's key. But then, and this is the really critical part, we're going to look at what happens next. How this sudden abundance of a super hard material is quietly revolutionizing everything from semiconductors to deep space optics.
It's a huge story, the industrial grit part. Because the mental image we have of a lab-grown diamond is all wrong, isn't it? It's not a sterile lab in Silicon Valley.
Not even close. It's night and day. This is heavy industry. Think steel mills, not clean rooms.
I want to talk about this one story that really brought that home for me. It's about a man they call Master Chen. He's a veteran technician in Zhuchang.
Right. He's been there from the beginning, or close to it.
40 years. He has spent 40 years of his life listening to this sound, this rhythmic, heavy thrum of the cubic press. He said you feel it in your bones before you hear it.
The sound of immense pressure.
Exactly. And in the 1980s, his world was gray. It was gritty. He described the air being thick with graphite dust. He wasn't making jewelry. He wasn't even thinking about it. Teeth.
Industrial teeth. That's a very literal description.
Diamond grit, the stuff they embed in saw blades to cut through granite, or the tips of drill bits for coal mines and oil rigs. He was making the tools that were building modern China.
So to him, this machine, the high-pressure, high-temperature press, it wasn't a creator of dreams.
No, he called it a beast of burden. It was just a tool. He said something that really stuck with me. He said, the machine didn't care if it made dust or a jewel, the physics are the same.
Rightful. The machine has no concept of value, only of process.
Right, and then you fast forward, there's this recent clip of him standing next to one of the newest generation presses. It's more automated, but it's fundamentally the same beast.
Same principle.
And he watches as the operator opens it up, and instead of a tray of gray, gritty dust, they pull out this rough stone, a 10-carat stone. He described it as looking like frozen light.
From gray dust to frozen light, that's the entire 60-year journey in one image.
And what's fascinating is his reaction. He wasn't romantic about it. He just nodded. He said the only difference between the grit and the glory was patience. The state-backed patience that allowed them to perfect running the machine for a week instead of just an hour.
That manufactured persistence is not a lucky breakthrough. It's the result of a deliberate, long-term industrial policy. Which brings us to the geography of it.
The triangle. Zhengzhou, Changshan, Kui. Why there? Of all places in China, why this agricultural region?
Right. It wasn't a tech hub like Shenzhen. It wasn't a financial center like Shanghai. To understand why, you have to look at a specific town inside that triangle. Zhejiang.
Okay.
Today, Zhejiang is called the diamond capital of the world. It produces something like 95% of China's synthetic diamonds.
And China produces, what, 80% of the world's?
Roughly, yes. So this one small county, Zhejiang, is effectively the global center. But if you went there in the 1970s, it was a totally different world. It was a traditional agricultural county. It was famous for chili peppers and beef cattle.
So you go from farming chilies to synthesizing the hardest substance in the universe. That is not a normal industrial leap.
It's not. And it wouldn't have happened without a seed that was planted by the state. That seed was the Zhengzhou Abrasives Research Institute.
This was a government institute.
Correct. It was founded way back, late 50s, early 60s. Text, 1963 is the key date here.
That's the year they made the first successful synthetic diamond in China.
Yes. And think about what was happening in 1963. The Sino-Soviet split was in full effect. China was isolated. It couldn't get technology from the West, and now it couldn't get it from the Soviet Union either.
So they were on their own.
Completely on their own.
Yeah.
And they had a massive country to industrialize. You can't build bridges, you can't drill for oil, you can't build an army if you can't cut hard metal. And to cut hard metal, you need industrial abrasives, you need diamonds.
It was a matter of national security, strategic independence.
Absolutely. It was never about luxury. It was about survival. So the government poured immense resources into this institute in Zhengzhou. And they made a crucial decision. They bet on a specific piece of technology.
The cubic press.
The cubic press. The West and De Beers, they were mostly using something called the belt press. The Soviets developed their own thing, the bars press. But China went all in on the six-sided anvil press.
Okay, let's break this machine down, because it sounds like something out of science fiction. Cubic press.
It's an engineering marvel that looks, on the surface, sort of brutally simple. Imagine a small cube at the very center. This is your reaction chamber.
Right, where the magic happens.
Now imagine 6 massive steel anvils, huge, specially forged pieces of metal. One pushes from the top, one from the bottom, one from the left, one from the right, one from the front, and one from the back.
Like the faces of a die all pushing inward.
Exactly. And they're all driven by enormous hydraulic cylinders. And they all have to press inward at the exact same time, with the exact same force. If one is a microsecond off or a tiny bit weaker, the whole thing can just blow apart.
And the forces are astronomical.
We are talking 5 to 6 gigapascals. That's about 60,000 times the atmospheric pressure at sea level.
That's a number that's hard to even comprehend.
The classic analogy is balancing the entire Eiffel Tower on the tip of your thumb. That's the kind of pressure concentrated in that tiny chamber. And at the same time, you're heating it up to about 1,500 degrees Celsius.
So you've created a tiny piece of the Earth's mantle in a factory in Henan.
That is precisely what you have done. And for decades, Western engineers looked at this design and said, it's too complex, it's too unstable, the alignment is a nightmare. And they weren't wrong. It was a nightmare.
But Henan persisted.
They did. And this is where the story pivots from a state-level project to a grassroots industrial cluster. In the 1980s, you had these engineers from the Zhengzhou Institute, guys like Feng Jinzan, who started going back to their hometowns in places like Zhejiang.
The Sunday engineers, I read they were called.
Right. They work at the state lab all week. Then on the weekend, they go to these small rural workshops and teach local farmers and entrepreneurs how to build and operate these presses.
That is just a wild image to me. A bunch of chili farmers learning about gigapascals and hydraulic synchronization.
But it created this incredibly resilient ecosystem. Because the machines were so difficult to build and maintain, everybody had to become an expert. You couldn't just call a service technician from Germany. You had to learn how to fix it yourself.
So you get this entire generation of skilled workers who know these machines inside and out.
And that creates the vertical integration that is their secret weapon.
Explain what that means in this context.
It means that in Zhejiang, they don't just make diamonds. They make the machines that make the diamonds. They forge the steel for the anvils. They mix the graphite powder for the raw material. They write the software that controls the hydraulic pumps.
So if an anvil cracks in the middle of a production run,
You don't put in an order to a supplier in another country and wait 6 weeks. You call your cousin who runs the forge down the road, and you have a new one by the next morning.
the iteration cycle is almost instantaneous.
Exactly. While a lab in the West is waiting for a spare part, a factory in Zhejiang has already tried 10 different solutions, failed 9 times, and found one that works better. They are learning and improving at a pace that is impossible to compete with.
They basically open sourced the technology among themselves and drove the cost into the floor.
And they achieved a scale that is just mind-boggling. We're not talking about a factory with a dozen machines. We're talking about single companies like Huifeng Diamond or Power Diamond that operate thousands of these presses.
It's a server farm for carbon.
And that scale, that mastery over the process for making cheap industrial grit is what set them up for the big pivot.
To gem quality stones.
Right. Once you have 1,000 presses running perfectly for an hour at a time, you can afford to take one of them and say, let's see what happens if we let it run for 100 hours.
But that seems exponentially harder, keeping that insane pressure and temperature perfectly stable for a week.
It requires incredibly sophisticated control systems, sensors, software. But again, because they built the machines themselves, they could tweak and refine them. They weren't locked into a vendor's proprietary system. This is what we call the legacy advantage.
Their past as a low-margin grit producer became their biggest strength.
They'd already paid for the factories, the power grids, the supply chains. That was all amortized over decades of selling industrial dust. So when the technology was finally ready to produce big, clear gems, their cost basis was almost zero.
So they didn't have to build a new industry. They just had to recalibrate the one they already had.
They pivoted from a high-volume, low-margin business to a high-volume, high-margin business, and they could undercut every other producer on the planet.
Which brings us right back to the consumer. Because all this industrial history, all these gigapascals and Sunday engineers, it all lands with a thud on a glass counter in a jewelry store.
It lands right in front of that young couple we read about in Shankui.
Yeah, let's replay that scene because it feels like the critical moment where the industrial reality meets the consumer myth.
It's the moment the dam breaks.
So you have this young couple, probably in their 20s. They're sitting in a small jewelry shop. In a velvet tray on the left, there's a natural diamond. It's got a GIA certificate, a story about being 1 billion years old, formed in the earth. And it has a price tag that's, say, 3 years of their savings.
The entire De Beers narrative distilled into one object.
Then, in the tray on the right, there's another stone. It was grown in a factory just a few miles down the road. To the naked eye, it looks identical. In fact, it might even look better. It's clearer, it's brighter.
More fire, more brilliance.
And the price tag is 1/10 of the natural one, maybe even less.
Right.
And you can see this moment of calculation in the groom's eyes. He realizes the only thing separating these two chemically identical objects is a story. And he decides the story isn't worth 3 years of his life.
That right there is the collapse of information asymmetry.
Unpack that term.
For a century, the diamond business was built on it. It means one party in a transaction, the seller, has vastly more information than the other party, the buyer. You, the buyer, had no way of knowing what a diamond was truly worth.
Yeah.
You had to trust the jeweler. You had to trust the brand.
The price was high because they told you it was rare.
And you had no way to verify that. The entire concept of scarcity was a marketing invention by De Beers. They controlled the supply, so they could create the illusion of rarity.
But now technology has just demolished that information gap.
Completely. With the $50 gadget you can buy online.
The handheld spectrometer or diamond tester, how does that little pen actually work?
It's surprisingly simple physics. The most common ones test for thermal conductivity. Diamond is one of the most thermally conductive materials on Earth. It pulls heat away incredibly fast.
So the probe heats up.
The probe has a tiny heated tip. When you touch it to a stone, it measures how quickly the heat is wicked away from the tip. If you touch it to glass or cubic zirconia, which are insulators, the heat stays there, the machine stays silent.
But if you touch it to a diamond,
the heat is instantly sucked into the stone's crystal lattice. The tester detects that rapid temperature drop, and it beeps.
if you touch that probe to the billion-year-old natural diamond, it beeps. And if you touch it to the 1-week-old Heenan diamond,
it beeps exactly the same. Because to the laws of physics, carbon is carbon. The machine doesn't care about a romantic backstory. It only cares about the atomic structure.
This gets back to that ice analogy I saw in the research.
It's the most perfect analogy there is. Let's say you're having a party and you need ice for drinks.
Okay.
You have two choices. You can hike up to a glacier, find some ancient 1,000-year-old ice, hack off a chunk with an ice axe, and carry it home. That's your natural ice. It's got a great story. It might have some air bubbles or bits of dirt trapped in it.
The inclusions in a natural diamond.
Or you can go to your freezer, which uses electricity and technology to freeze filtered water into perfectly clear, uniform cubes. That's your lab-grown ice. Now, when you put them in a glass of whiskey, is the drink colder with the glacier ice? Is the chemical composition H2O any different?
No.
The only difference is the narrative. And what the market is saying very loudly is that for most people, the narrative isn't worth a 90% price premium. They just want a cold drink.
They just want a sparkly stone. But the Western lab-grown companies, they try to create a new narrative, don't they? They push their CVD method as being superior.
They try to position their technology as being cleaner, more high-tech. They try to imply that Heenan's HPHT method is old or brute force or somehow less pure.
So let's get into the weeds on this. HPHT versus CVD. Why is this the new front line in the diamond wars?
Okay, so CVD stands for chemical vapor deposition. It's a gas-based process. You take a tiny sliver of a diamond, a seed crystal, and you put it in a vacuum chamber.
Like a high-tech oven.
A microwave, almost. You fill the chamber with a carbon-rich gas, usually methane, and you blast it with microwaves to create a plasma. In that plasma, the methane molecules break apart. The carbon atoms then gently float down and settle onto the seed crystal layer by atomic layer. It's like a very, very slow, very precise snowfall.
Elegant.
It is elegant,
Huh.
but it has flaws because it's a low-pressure process. The crystal structure that forms isn't always perfect. You get vacancies, which are basically tiny holes in the lattice where a carbon atom is missing. And sometimes other atoms, like nitrogen from the air, get trapped.
And what does that do to the stone?
It gives it a color, usually a brownish or yellowish tint. Most CVD diamonds come out of the reactor with this off color.
So they're not the perfect icy white we expect.
Actually. So to get rid of that color, they have to do a post-growth treatment.
Oh.
And this is the ironic part. They often have to take their superior CV diamond and put it into an HPHT press.
Hey.
They use high pressure and high temperature to essentially squeeze the defects out of the crystal and improve the color. They use the Heenan method to fix the flaws of the Silicon Valley method.
That completely upends the marketing story.
It does. Now let's look at HPHT, the method Heenan has perfected. It's not a gas process, it's a liquid phase process. You have your seed crystal at the bottom of the chamber, a carbon source like graphite at the top, and in between, a molten metal alloy.
A metal soup.
Usually an iron-nickel alloy.
Right.
Under that immense pressure and heat, the carbon dissolves into the molten metal at the top, and then because of a temperature gradient, it precipitates out of the solution onto the cooler seed crystal at the bottom.
It's growing from a liquid.
And because it's growing under 60,000 atmospheres of pressure, the crystal lattice is forced into a near-perfect, incredibly dense structure. There's no room for vacancies or impurities.
So it comes out white.
It comes out as D or E color grade.
Right.
The highest grades of colorless, no post-treatment needed. It's structurally more sound and aesthetically more perfect straight out of the press.
And there's also a difference in the shape it grows in, right? The crystal habit.
A huge difference. CVD grows in a flat, square plate, like a wafer. You lose a lot of the material when you cut around brilliant from a square plate. HPHT, however, grows in a shape called a cuboctahedron.
Okay.
It's a beautiful 14-sided shape, a combination of square and triangular faces. And it's significant because that is the natural growth shape of diamonds deep inside the Earth's mantle.
So the brute force industrial method is actually creating a crystal that's structurally more similar to a natural diamond than the elegant high-tech method is.
In every meaningful way, yes.
Yeah.
It's a superior method for producing gem-quality material at scale. It's not just cheaper, it's better. And that combination of better and cheaper is what's causing the economic earthquake.
Let's talk about that price crash, because it's not a slow decline, it's a cliff.
It's a free fall. Just a few years ago, a 1-carat, good quality lab-grown diamond, might have been $4,000 or $5,000, a nice discount from a natural one. Today, you can easily find a stone of the same quality, or better, for under $1,000. In the wholesale markets in Zhengzhou, those stones are trading hands for a few $100s.
And this leads us back to the woman from the intro and the resale trap.
This is the dirty secret of the natural diamond industry right now. For generations, they sold diamonds as an investment, a store of value, and that value was implicitly pegged to the replacement cost.
If you lost your ring, what would it cost to buy another one just like it?
Exactly. And for 100 years, the answer was you had to buy another expensive natural diamond. But now the replacement cost has been reset. If you lose your 1-carat natural diamond, you can replace it with a visually and chemically identical lab diamond for $800.
So why would anyone pay you $5,000 for your used natural one?
The secondary market has collapsed. The floor price for all diamonds is now being set by Henin's factories. The investment value of 99% of natural diamonds has effectively gone to zero.
That is just a brutal reality for anyone who bought into the myth. But as I was looking at all this, I got the distinct impression that Henan doesn't really care about the jewelry market anymore.
They don't. It's already won.
It feels like the jewelry business is just a funding mechanism for their real goal. It's just the appetizer.
It's the cash cow that's financing the real revolution.
Sure. Because I read this profile of a young thermal physicist in a Zhengzhou lab, and his perspective was completely different. He wasn't looking at these perfect crystals as gems.
He was looking at them as the ultimate semiconductor.
Exactly. To him, the fact that these cubic presses can churn out tons of flawless single crystal diamond isn't about making affordable earrings. It's about solving the biggest problem in modern electronics.
Which is heat.
Heat. Why is heat the great enemy?
Because every single electronic process generates it. Every time you push an electron through a silicon chip, there's resistance. That resistance creates heat. It's the friction of the digital world.
And if you can't get rid of that heat,
your chip overheats and either shuts down or melts. It's the fundamental bottleneck. It's why your phone gets hot when you're using GPS, why your laptop fan screams when you're editing video, and why Google has to build data centers next to giant rivers. Cooling is everything.
And diamond is the solution.
Diamond is the ultimate heat sink. It has the highest thermal conductivity of any material known. It's 5 times more conductive than copper, which is what we use in the best heat sinks today.
So if you build a chip on a thin wafer of diamond,
the heat just vanishes.
Yeah.
It's wicked away from the transistors instantly. This means you can run the chip much faster and pack the components much closer together without it melting.
So faster computers, smaller devices.
The real game changer is how diamond handles high power. And for that, we have to talk about something called band gap.
Okay, ultra-wide band gap. I saw this term everywhere. Explain it like I'm not a physicist.
Okay. Think of the band gap as an energy wall. For a material to conduct electricity, its electrons have to get enough energy to jump over that wall.
A hurdle.
A hurdle, exactly. In silicon, the material in virtually all our computer chips, that hurdle is very low, about 1.1 electron volts. It's easy for electrons to jump over, which is why it's a good semiconductor.
Yeah.
But it's also easy for them to leak over when things get hot or the voltage is high, the chip fails.
Okay. And the next step up from silicon is what? Silicon carbide?
Right. Silicon carbide or GaN, gallium nitride. That's what's in high-end EV chargers. Their band gap is higher, around 3.2 or 3.4 EV. A higher hurdle. They can handle more power and heat than silicon.
And diamond?
Diamond's band gap is 5.47 EV. It's not a hurdle, it's a skyscraper.
It's in a completely different league.
Yeah. It means you can hit a diamond-based device with enormous voltages, thousands and thousands of volts, and the electrons stay put. It doesn't break down. It doesn't leak. It just handles it.
So where do we see this being used? This isn't for my next iPhone, is it?
Not right away. Think bigger. Think national infrastructure, the power grid. We're trying to move massive amounts of renewable energy from solar farms in the desert to cities. We need circuit breakers and power converters that can handle 10,000 volts or more. Silicon devices literally explode at that level. Diamond can do it.
What about transportation?
Electric vehicles. A diamond-based inverter in an EV would be smaller, lighter, and could handle the current needed for 5-minute fast charging without overheating. It could revolutionize high-speed rail, electric airplanes.
And extreme environments. Space.
Absolutely. Space is flooded with high-energy radiation that degrades silicon chips over time. The diamond lattice is so strong, it's virtually immune to radiation damage. A diamond-based sensor could operate inside a jet engine, at the bottom of a geothermal well, or on a probe going to Jupiter.
So when we see that Henan is producing 80% of the world's raw synthetic diamond material, We shouldn't just be thinking they control 80% of the lab-grown jewelry market.
We should be thinking they control 80% of the foundational material for the entire post-silicon era of electronics.
That is a staggering strategic advantage.
It's the ultimate example of the red ocean versus blue ocean strategy. The jewelry market is a red ocean. It's full of blood in the water. The competition is savage. Prices are plummeting. Margins are being destroyed. Everyone is fighting over the same customer.
But the market for functional, high-powered diamond electronics.
That's the blue ocean. It's vast, deep, and wide open. The demand is practically infinite. Every AI data center, every 5G base station, every EV, every power grid on the planet is hitting a thermal and voltage wall. Diamond isn't just a better solution. It's maybe the only solution.
And Hainan is positioned to be the sole supplier of the raw material.
They control the capacity, and this is the absolute genius of their long-term strategy. They are using the money from the bloody red ocean, the profits from selling cheap rings, to fund the massive R&D needed to conquer the blue ocean.
So every time a young couple in America buys a $1,000 lab diamond ring, they are unknowingly subsidizing the Chinese research into diamond wafer manufacturing for military-grade radar systems.
Yes. They're keeping those thousands of cubic presses running 24/7. They're keeping Master Chen and his apprentices employed, perfecting the growth process, learning how to dope the diamond with boron to make it conductive. You can't learn that stuff in a university lab. You need industrial scale. The jewelry market pays for that scale.
It's a Trojan horse made of carbon.
It's a classic industrial playbook. Execute it to perfection. Start with the low-end commodity industrial grit. Dominate global volume and master the supply chain. Use that scale to move up the value chain to a consumer product jewelry. And then use the profits from that to leapfrog everyone into the next generation strategic industry.
It reframes this entire thing. We were so focused on the real versus fake diamond debate.
Which was always a distraction, a debate created by marketers. The real story was always about material science and industrial policy.
You know, it reminds me of the story of aluminum.
That's a great one.
In the 19th century, aluminum was rarer and more valuable than gold. Napoleon III served his most honored guests on aluminum plates because it was such a status symbol.
And then the whole Heroot process was invented. Electrolysis made it cheap to produce.
Actually, suddenly this precious metal became a commodity. We started wrapping sandwiches in it, making soda cans out of it. But, and this is the critical point, we also started building airplanes out of it.
Right. You can't build a 747 out of a material that's priced like a precious metal.
No. For a material to become revolutionary, it has to become abundant. It has to become cheap. The commoditization of aluminum is what enabled the aerospace age.
And what you're saying is, we are witnessing the exact same moment with diamond. As long as it's a precious gem, it's trapped in a velvet box, it's industrially useless. But once Hainan makes it as common as aluminum,
then we can start building the things we could only dream of before. The quantum computers, the fusion reactors, the interstellar probes.
We can pave the high-voltage roads of the 21st century with it.
So to bring it all together, what started as this sad story about a woman in a jewelry store, her asset losing its value, maybe we're looking at it all wrong.
Her personal loss is, in a way, a massive gain for society. We've just gone on this incredible journey. We started with her ring. We traced its loss of value back 60 years to a state-run abrasives lab in an agricultural county in China. We saw how they perfected this brute force technology, how they built an unbeatable industrial ecosystem, and how they used it to first conquer the jewelry market.
And now how they are pivoting that entire industrial engine toward the future of high-tech computing and energy.
It's the story of a luxury good being dethroned, and in its place, a strategic material being born.
We often worry about artificial intelligence or quantum computing as the next big disruptors. But perhaps we should be looking at the hardware that will make them possible. It turns out that the forever in a diamond isn't about a marriage proposal. It's about a 60-year industrial bet that is just now paying off. When the hardest material in the universe becomes as common as a silicon chip, the question isn't how much is it worth, but what can we build with it now that it's finally free?